Problem here, number 5, that we were given this curve 2 and then cosine 2 plus cosine k theta, and if we are going to do anything with the area here at all, we should take a look at the picture of it. So if we go ahead and put ourselves in polar mode, and we go 2 plus, I'm going to go ahead and do this just as theta here. So we'll just say what if k equals 1, let's see what this looks like. And if you look at my window here, I got 0 to 2 pi, and then I'm going to make my window here negative 5 to 5. I don't know if that's going to be big enough, but we'll find out. Alright, and we can see that 0 to 2 pi gave us the entire shape here. If we were to change it to 0 to, or 2 plus 2 theta, because again our general form here is 2 plus k theta, and we graph again, you'll notice that again the 2 pi is going to be the interval that will give us the entire picture again. If we did that with 3 theta, same deal. Okay. So no matter what k is here, it seems to be the fact that 0 to 2 pi is going to be the domain of choice here, if you will, to get us our full picture for theta. Again, pretty crazy curves, right? All right. So bottom line here is that if we look at it says show that the area of the region enclosed by the curve does not depend on the value of k. And what is the area? So again, the region of the area enclosed by this curve, okay, or the area of the region enclosed by the curve does not depend on k. If we let k equal 1 here, and we go from 0 to 2 pi, remember and when we're dealing with polar form, we have 1/2 times r squared is our general formula, and our 0 to 2 pi over here is our interval. So if we do our math 9 on that, and we do our 2 plus cosine theta, again we'll let theta equal 1, we're going to get 0 to 2 pi. Oops, forgot my x. Oh, I forgot my square now. Jeez. Type the thing in right would be helpful. And I got to multiply that by 1/2, of course. Alright, so we get this 14.37. Okay. Alright, let's see what happens. What happens if we change the value of k here? So if we go ahead and change the value of k to 2 theta instead. Same integral. We ultimately notice we get the same thing, don't we? And if we did it with a 3, just for argument's sake, we get the same thing. And remember, each of these needs to get multiplied by 1/2 to get the actual area. Okay. So you notice that, that no matter what that k value is, we seem to be getting the same result for the area part. All right. And ultimately, the question is there a way that we could show that that's true, okay, algebraically? Because again, showing it doesn't mean try 3 examples and, since it works for all 3, it must work for everything. And we know that we can't prove something by example. We got to prove it with algebra. So ultimately, if we were to take our integral, let's see if there's anything we can do with this. If we were to square that integrand as we have it, we would get 4, and then it'd be plus 2, actually plus 4, cosine k theta. And then if we square the cosine k theta, we'd get cosine squared k theta times k dx. And let's see what happens if we try to integrate term by term here. Let's go, the integral of 4 here is going to be 4x. The integral of 4 cosine k theta, the antiderivative of cosine k theta is going to be 1 over k sine k theta. ultimately, on this one, we could factor out a k. What about cosine squared of something? How are we going to handle that? Is cosine squared a known derivative? I mean, we can factor the k out because k is just constant, this k. But if we had cosine squared theta, is that a known derivative for us? The answer is, of course, what? No. So it's not a known derivative. And if we wanted to, we could write it as cosine k theta times cosine k theta, and then it would be in some kind of product form, which would indicate maybe an integration by parts problem. Okay. So we could try that. Okay. Because really, ultimately, is there any other option? So let's try it. Because like I said, the first two seem to work out real nicely. But if I had to integrate cosine k theta d theta, if I let my u be cosine k theta, and my dv be cosine k theta d theta, see what would happen. If we do du here, we would get negative k sine k theta d theta. And then v would be, if we anti-differentiate this, we'd get 1 over k sine k theta. Alright. And if we go uv here, we're going to get 1 over k cosine k theta sine k theta. And v du would be 1 over k sine k theta. And that would be that times this one, negative k sine k theta d theta. And ultimately, in working out this part, the k's here, of course, would make negative 1. These two would be sine squared of k theta. And we could take out a minus and then end up being plus. So it would be plus sine squared k theta d theta. And so at this point, we wind up essentially kind of in the same boat here. True? Alright. So if you remember what we do with integration by parts, if we wind up in the same boat like that, as we try it one more time here, because this is a situation where it may work, that if we go u again and we go sine k theta, and dv is sine k theta d theta, du here being k cosine k theta, v being antiderivative of sine here would be negative 1 over k cosine k theta. So this time if we do our uv here, we get negative 1 over k sine k theta cosine k theta minus integral of v du would be negative 1 over k cosine k theta times v du would be k cosine k theta d theta. Yeah, space here, but okay. So that looks pretty daunting at this point. But remember, here's what our answer looks like right now. It looks like the integral of cosine squared k theta, which is what we started with, is equal to 1 over k cosine k theta sine k theta minus 1 over k sine k theta cosine k theta. And right off the bat, what does that do for us? Yeah, those are gone, which is nice. And so ultimately we have integral of cosine squared k theta on this side, d theta, is equal to what we have over here, which would be negative. And if we put these two together, again, the k's are going to cancel out. And we have cosine squared k theta d theta. So what does that do for us? Okay, normally what happens, remember, is this. We're going to end up with something else plus this, and then we can add this to both sides and have two of them, and then we'll divide by 2 to get that integral alone. Okay. But in this particular case, we wound up back with essentially nothing because these two things canceled out. Again, just make sure we have the signs right on here. If we did our u, v here, our v again, the antiderivative cosine is sine, so this is positive, so it's going to be positive. When we do it in this one, it is negative because the antiderivative of sine is negative cosine. Okay? So we wind up with that, and ultimately we put that together, those two cancel out, which is essentially a problem because then we, again, with this v to u part, we have a negative negative, which makes it a positive. Okay? And so we just wind up with this, which we know is a true sentence, but it really doesn't solve anything for us, then, does it? So, with that said, I guess the question is there an algebraic way that we can find the cosine squared of k theta antiderivative? Because if we could, we ultimately, could show that, that this doesn't depend on k. We could put in our 0 and 2 and we would likely get that same answer every time, whether k was 0, 1, 2, 3, 4, 5, 6, whatever the case may be. Okay. All right. For time's sake here, I'm not going to get into that anymore for the time being. I do want to mention, though, that the other two parts from that, the part B and the part C, if you have not done those already yet, we'll finish those tomorrow, depending on our time. And then we did have a little bit of number 6 to finish as well, so we'll finish that on a different occasion as well.